welcome you to my lecture today. Of course, today the focus is going to be on multivariate normal density. I remember earlier in the week, we started normal distribution. I've walked you through univariate normal. We've done bivariate normal, and of course, today we actually want to generalize normal density to situation where we got more than two variables. Okay, so situations where we got more than two variables and they are normally jointly distributed. Of course, the idea of multivariate normal density is going to work. Okay, so this is the outline. We've been following this since Monday. Like I said, we've done univariate, we've done bivariate, and of course, today the focus will be on multivariate. I'll four of us walk you through the distribution form. I'm going to talk about probability calculations, affine transformations, conditional distributions, all the way to parameter estimations. Okay, so let's get started. Okay, I want to show you multivariate normal density. Now, if you take a look at equation 12, if I have x equal, I got x1, x2 up to xp, where, those represent features, okay? And of course, if they follow multivariate normal, okay, the probability density function associated with the joint occurrence of the variables is what is given in equation 12. Whenever we ask you to write the density function of a multivariate normal, okay, what you're going to write is equation 12. Okay. Now, just like a typical normal density, I remember the other time when I was walking you through the univariate density, normal density, we got two parameters. Okay. The two parameters are mean and variance. Okay. In the multivariate setting, we also have parameters. Okay, the parameters here is going to be the mean vector and the variance covariance. Okay, and that is the reason why if you take a look at, give me 1 second, I'm going to use mine. Okay, so if you take a look at this guy now, that is actually giving you a mean vector. Okay, I'm going to have me1 up to me p, depending on the number of, variables that I have. Then I'm also going to have covariance matrix. The say covariance matrix. The covariance matrix is always going to be a square matrix. I'm going to say that again. The covariance matrix always going to be a square matrix. Okay, the square matrix, the numbers of rows and the numbers of columns, okay, they're going to be the same. They're going to be the same. Okay, now when you take a look at what I have, this is a variance, covariance matrix in the diagonal. You have the variances. In the half diagonal, you have the covariances. So if I want to write in a short form, okay, if I write a random variable x, follow normal distribution. When you take a look at this, I mean the vector of mean. When you take a look at this, I actually mean the variance covariance matrix. You can also write it in this form, indicating, when you have n subscript p, you try to tell the world the numbers of your features is p. Is there any question on this page? Because we are getting into highly complicated, what we're going to be doing from now will be mathematical intensive. But the moment you pay attention and you know, we can relate this to real life practical situation, you actually going to be fine. Okay, now if you take a look at what I have on this page, I actually want to talk about some multivariate normal properties. Okay, and the properties are more or less like we want to place a restriction, we want to place some kind of restrictions on the mean and the covariance parameters. Now, let me tell you this. When I'm working on the mean that I call mu j, okay, me can take on any values, okay, in real number. Me could be zero, me could be negative, me could be positive. That's no problem about that. Okay, but when you are talking about, if you take a look at the second one, that is the variance. The variance, don't forget, variances occupy the diagonal of a covariance matrix in multivariate analysis. It is required that the variance has to be greater than zero. Okay, we are ruling out situation here where variance can be negative and where variance can be zero. That situation is not going to happen. That's what we mean. In case you are computing and you actually get maybe a negative value for variance, or you get a zero for variance, then check your computation. Okay, now the sigma ij, on the other hand, is a particular covariance. Whenever you see sigma I subscript j, I not equal to j, then we are actually talking about covariance. When you see a sigma where they have jj or they have ii, then you're referring to variance. Variance is a variation within. Covariance is a variation between. Does that make sense? Now, the sigma ij here is multiplying the correlation by by the product of the standard deviation of the respective variable. Okay, and of course by Cauchy's or Cauchy's squash, okay, we expect that the square of the covariance has to be less or equal to the product, okay, the product of the variances. That's what we mean. Okay, now, and you remember the other time we talked about positive definite. Okay, we actually want to be using that idea now. We want to be using the idea of positive definite. Let me tell you this. When I have a variance covariance matrix, which is this guy, variance, I used to call it variance covariance matrix. Why did I normally, I'm referring to this particular guy here. I call it, some professors call that covariance matrix, but I can call it covariance matrix. I can call it variance covariance matrix. Why? Because in the diagonal, I have the variances. In the off diagonal, I have the covariances. And that's why I call it variance covariance matrix. But you can simply call it covariance matrix. That's no problem. Okay, now, do you know that if I have a variance covariance matrix, I should be able to obtain the generalized variance. The ongoing assignment talk about generalized variance. The generalized variance is you trying to figure out the determinants of the variance covariance matrix. The generalized variance is different from total variance because the total variance, even though the two of them measure spread in data set, but the total variance ignore covariance, or we ignore relationship between the variables. But the generalized variance does not ignore relationship, and that is the reason why in statistical world, okay, the generalized variance is actually is being used. Now, the generalized variance is a determinant of the variance covariance matrix If I'm able to find the determinant of the variance covariance matrix, then I will be able to find the inverse. I'm going to say that again because if I want to answer some inference question, then I actually need, the knowledge of the inverse of the variance covariance matrix. There is no way I'm actually going to pass through. There's no way I'm going to get to inverse of a variance covariance matrix without first passing through the determinant of the variance covariance matrix. Mathematically speaking, if I want to obtain the inverse of a matrix, that matrix, for inverse to exist, that matrix must not be singular. Must not be singular means the determinant must not be equal to 0. Because when the determinant is, and the determinant must not also be very close to 0. If the determinant of the variance covariance matrix is very close to 0, then it means the variables are highly correlated. And when they are highly correlated, then it's going to create an interpretation issue. Does that make sense? Okay, now when we should be able to take a look at that. And what we're trying to emphasize here is that the inverse of the variance covariance matrix must exist, and the variance covariance matrix itself is assumed to be a positive definite. And you remember the idea of a positive definite will be used when we are trying to figure out the variance of a linear combination of random variable that follow normal distribution. Okay? Now, I needed to pay attention. Now, if I want to look at the variable one at a time, okay, one at a time, okay, I'm actually talking about marginals density. Okay, this particular the variable follow normal distribution. It has its own mean and its variance. Another one follow normal distribution with its own mean and with its variance. That was what we did on Monday. Now, I needed to pay attention to this page. If I have so many variables, x1, x2, up to xp, okay, and let me tell you this. If x1, maybe x1 represent height of my patient, s2 represent weight of my patient, happens to be a medical doctor, okay, and x3 represent the blood pressure. If I have x1, s2, s3, for instance, okay, or I have more, and I really want to figure out what is the percentage of my patient, okay, with blood pressure between this and that. I also want to figure out simultaneously what is the percentage of my patient with the height between this and that. What is the percentage of my patient with the weight between that and that. I want to figure that out simultaneously. That is what equation 13 is talking about. If I have P number of such variables, I'm actually going to have P numbers of integrals. Then I'm actually going to perform an antiderivative, okay, sequentially. It's not just going to be one time, but I got multiple integrals involved. When you see integral in statistics or in mathematics, don't be scared. You know what integral is trying to talk about. You want to figure out the total, the area under a particular curve, and you want to look at what is the percentage, okay, that falls within, the interval. That's what you mean. Okay. Now, that's exactly what we mean in the question 13. And of course, the CDF, because equation 13 is a PDF. Of course, CDF also exists. The CDF is, I want to look at the range, I want it to accumulate, to start from the lower part to a particular point that I'm interested in. Okay, that's why you're actually seeing the upper, in the integral, the upper value, go to x1 from negative infinity to x1. X1, I will be the one that will determine that. Okay, I want it to stop at a particular point. Okay, cumulating from negative infinity, cumulating from the lowest point ever to a particular point of interest. Then I'm actually focusing on cumulative density function. Okay, now this particular page is very, very crucial in statistical inference. Okay, and I need you to pay attention to affine transformations. Very, very useful. Okay, suppose that I have random variable x, x1, x2 up to xp, and we have already investigated maybe using graphical approach, or we go by way of uh, test, because we have multivariate normality test. Okay, now whether we go by way of Madia test or we go by way of energy test, I'm still going to discuss how we can investigate whether data set follow multivariate normal distribution. We don't just assume that it follow multivariate normal distribution. Let me tell you this. Even if each variable follow normal distribution on their own, okay, that does not mean collectively or jointly they're going to be normally distributed. I'm going to say that again. Even if each variable on their own, maybe you look at the histogram, or you look at the density plot, or you look at the stem and leaf plot, or you look at the box plot, okay, or you conduct a normality test on each variable, and you realize that each variable is normally distributed, that does not necessarily translate into multivariate normal distribution. We also need to check. We have several tests that can be conducted for that. One of them is Madia test. Another one is energy test. But I'm gonna review that as time goes on. But you know what? What I need you to do here, I need you to pay attention. Now, X follow, X is X1, S2 up to XP, and this follow multivariate normal with the mean vector mu and the variance covariance that. Of course, this is the dimension of the mean. This is the dimension of the covariance matrix. Now, I want to come here. Let's assume that we have a matrix A, and that matrix A may be a constant, okay, and it's n by P. And we have another matrix B that is also constant, okay. And with this, if I really want to generate a linear combination, I need constants. Constants actually gonna act as weight. Okay, now when you take a look at this, I want to define a random variable, a new random variable W, and this W is depending on X. This is the linear combination. W equal AS plus B. This is looking like a typical linear model in mathematics or statistics, or equation of a straight line, where you have slope and intercept. It's looking like that. Now, when you take a look at this right now, okay, now maybe I want to answer a question that has to do with statistical inference. Maybe I want to figure out if X follow normal distribution like this. This is the mean vector. This is the covariant structure. I want to figure out the mean of W. W depending on S. I also want to figure out the variance of W. Okay, now the mean of W is this, A mu. I will multiply the constant matrix by the mean vector. That will give me the mean of W. How do I figure out the variance of W? When I say variance of W, okay, don't forget the variance of W would, since W is depending on X, since W depending on X, and don't forget X is multivariate in nature, right? So multivariate in nature, if W is depending on X, the variance of W will be depending not only on the variance of S, but also going to be depending on the covariances of S as well. Does that make sense? I'm going to say that again. I want to figure out the variance of W. To be able to figure out the variance of W, as you can see in the model right now, W depend on S. And the S that we are talking about, it is not univariate. The X we are talking about, take a look at the X here. The X is X1, S2, up to XP. Now, if I want to figure out the variance of W, then the variance of W will depend on variances of X and their covariances. And if I want to rewrite that, this is how it's going to be. Take a look at that. Now, what am I trying to talk about? Take a look at this guy right now. Okay, if W equal to this, the mean of W is going to be A mu plus B. The variance of W is going to be A covariance A transpose. Now, if you take a look at this guy in the middle, that guy in the middle, okay, will give us both the variances and the covariances of X1, S2 up to XP. Does that make sense? Okay, now, before moving forward, I'm actually going to give you an example now from medical field. Let me say this. We are trying to take a measurement on cholesterol level of patients that are suffering from heart attack. Okay, suffering from heart attack. Okay, and of course, um, we want to consider three different days. Okay, a 0 day after 0 day, 2 days, 4 days. Okay, we want to measure the cholesterol level. They've given them treatment, and they actually we want to reduce the cholesterol level. Okay, now I needed to pay attention. I know because they have n observation, like the number of patients, maybe 20, 50, whatever, they can find the average for that, right? The average for the 0 day, okay? After 2 days, they find the average of cholesterol level again. After 4 days, they find the average of cholesterol level, okay, in that regard, okay. That is going to give me the mean vector. Now, the mean vector that I'm actually going to have, the first value will be the mean cholesterol level for 0 day. The second mean will be the mean cholesterol level for second, for after 2 days, and the other one will be after 4 days. Now, don't also forget, there's also going to be covariance matrix for each day. Okay, the covariance matrix is going to be 3 by 3, where I'm going to have a 0 here for 0 days, for 2 days, for 4 days. Don't forget that. Then I'm going to have 0, 2, and 4. Okay, if you take a look at here in the diagonal here, that will be the variance of the cholesterol level for day 0 here. That will be the variance for cholesterol level after 2 days, and that will be the variance for cholesterol level after 4 days. Then in the off diagonal will be the covariances. Does that make sense? Is that making sense? Okay, go ahead. Oh, you're not seeing that. Sorry about that. I can see. Okay. Let me see. Okay. Thank you for I'm seeing it here. I'm gonna repeat that. Sorry about that. Give me 1 second. Uh Let's see if this is gonna work. Give me 1 second. Actually, you're gonna use another one. Do you see that one? Oh, okay, that one is good for me now. Okay, now this is what I'm saying. 0 day, okay, 2 days and 4 days. Okay, this patient, they have heart attack. Okay, and you measure their cholesterol level. Okay, following the heart attack, you're giving them treatment, and the essence of the treatment is to reduce the cholesterol level. And of course, in the 0, okay, you measure the cholesterol level. You have a value for that. For the mean, don't forget, it's not one patient. There's so many. I'm expecting them to have different cholesterol level, but I'm going to find the average. Okay, I will do that for second day for that. Then with that, what am I going to have? I'm actually going to have 3 separate means that will become a mean vector, right? Then I'm also going to have the variance, covariance, matrix associated. I told you the other time, whenever average is involved, variance will be involved. And when variables are more than 2, covariance is also going to be involved. Now, what I'm going to do, okay, 0 day, 1 day, oh, sorry, 0 day, 2 days, 4 days, okay, then I'm going to write that. I'm going to write this, then 0, 2, 4. Now, here, that is the variance of the cholesterol level in the 0 day. Here, that is the variance of the cholesterol level after 2 days. Here, that is the variance of the cholesterol level after 4 days. In the half diagonal will be covariances. Does that make sense? Okay, now do you know I may want to ask a question? This is where affine transformation is going to come in. Let's say, for instance, I actually want to find the difference between cholesterol level in day 0 and after 2 days. Please pay attention. I want to find the mean of the average of the difference between the cholesterol level in day 0 and after 2 days. With that, I'm seeking to obtain the mean. If I'm seeking to obtain the mean, I'm actually going to use this guy, A mu. And in that regard, my A is a constant. Please pay attention. My A is a constant. If my A is a constant, this is what I'm going to do. Since I want to look at the difference for 0 days and 2 days, I'm going to call this one in my matrix A. Please pay attention. In my matrix A, I'm actually going to call 0 day 1. Then the after 2 days negative 1. Then 4 days 0, because I'm not interested in 4 days. I said I want to figure out the difference between the cholesterol level for 0 days and after 2 days. Then the weight, the element in my matrix, the element in my matrix is going to be 1, negative 1, 0. Does that make sense? 1, negative 1, 1 for 0 day, negative 1 for 2 days, is 0 for 4 days. I'm not interested in 4 days. Now, if I want to find the mean right now, I'm actually going to use this particular A to multiply the mean cholesterol level that I generated the other time. Does that make sense? And that will be A mu. So which means 1 minus 1, 0 as a matrix, multiply by the column mean. And that will give me the difference. How am I going to get the variance associated with that? If I want to get the variance associated with that, I'm actually using this guy. Look at that. My A, okay, my A, I said 1, negative 1, 0. Okay, give me 1 second. I think I'm going to, okay, I said 1, negative 1, 0. Okay, this is A now. Okay, multiply. Don't forget, there's going to be a 3 by 3 matrix, which is the covariance matrix. Then another one is going to be a transpose of A. Okay, it's going to be a transpose of A. So it's going to be 1, -1, and 0. This is going to give me the variance of the difference between the cholesterol level, after 0 days and after 2 days. If I want to change it to between the cholesterol level after 2 days and after 4 days, my covariance structure is not going to change. But you know what is going to change? It is matrix A. This time around, okay, this is going to be 0. Okay, let me use this to erase it. Give me 1 second. I want to change my constant matrix now because right now I'm only focusing on 2 days and after 4 days. Okay, if I'm focusing on 2 days and after 4 days, it means 0 for 0 day. I'm not interested in that. Then I'm going to put 1 here. I'm going to put a -1. Then this is going to be 0. This is going to be 1. This is going to be -1. Any question? Okay. Now I want to move into conditional, multivariate conditional distribution. We did the same under bivariate. There's possibility. Under bivariate, since we got 2 variables, okay, and we may be interested in if I have information about X, on average, what can I say about Y? But in a univariate case, if I have information about, for instance, okay, take a look at this. If I have information about okay, if I have information about the cholesterol level at the 0, and I have information about cholesterol level after 2 days, then on average, what would be the cholesterol level after 4 days? That's a conditional. I'm conditioning a variable given so many other variables. Does that make sense? Okay. The same way a doctor may want to okay, you know what? If I know the height of my patient and I know the weight of my patient, what can I say on average on the blood pressure of my patient? That's a conditional I'm actually going to use. And that is why question 15 is talking about, okay, but this time around, your X here, please pay attention. Your X here is X1 up to XP. Your Y here, Y1 up to YQ. The conditional is actually function is going to be the f of y given x. Don't forget the s that I'm talking about is several variables. Okay, it's going to be equal to the joint. Okay, the probability of the joint divided by the marginal. Take a look at that. Okay, now it's becoming complex. It's becoming complicated. And I need you to pay attention now. Okay, I need you to pay attention now. Okay, this guy is the conditional density that we're talking about. This guy is going to be the joint, and this is the marginal. Okay, pay attention to that. It's marginal. Okay, now I want to apply that in multivariate normal density now, and I want us to pay attention now. Pay attention now. Okay. I'm not necessarily going to finish this material today because I have to take a cool. There's a lot of mathematical complexity here, which I really want to spend my time on. In case you don't understand, please, I need you to ask me question. Okay, now let's get started. If a z follow a multivariate normal density, okay, with a mean vector and variance covariance, don't look at that theoretically. I always want you to view that practically, be taking that mean to be the mean, maybe the mean of blood pressure, the mean of weight, the mean of height, and the variance covariance to be the variances of each of the variable and their covariances. Okay, now, and let me tell you this. This very Z is a combination of X and Y. You know what? X from X1 to XP, Y from Y1 to YQ. There's so many. Okay, now if I want to talk about the mean of Z now, the mean of Z now, okay, here inside this, that guy itself is a vector. The mean prime of S is a vector. It's a vector mean for each variable S. Please pay attention. Then this guy now, this guy here, that's a vector mean for each variable Y. It's like, and if you now take a look at this guy now, oh my God, this guy is a vector that has another vector as a component. Can you see what I'm saying right now? That very mu is a vector on its own. And inside the parenthesis, the mu prime s is a vectors of means. And the mu prime y also vector of y. Are you following? You're following, right? Okay. Let me tell you this. I understand my math because I'm not just seeing notation, but I'm seeing reality. I'm relating. That's where I understand that. Now, when you take a look at that now, and that is the reason why I decided to further give explanation that this guy is this. Can you see that? And this guy is all of this. Can you see that? Because the mean vector, inside the mean vector, we have vectors inside a mean vector. Then inside covariance vector, covariance matrix, we're also going to have a covariance. We're also going to have another covariance matrix inside covariance. And this is what I'm going to show you right now. Please pay attention. This guy will be the general covariance. Oh my God, this guy is going to be the covariance matrix for variable x1 to xp. When I say covariance matrix for variable x1 to xp, that is going to be a square matrix p by p. Does that make sense? Then this guy here, also going to be a covariance matrix for variable y1 to yq. Depending on the numbers of variable y, okay, it's also going to be a square matrix. That's a q by q. Can you see that? And of course, he in the off diagonal, this guy, okay, is actually going to be another covariance matrix of p by q. Please pay attention. And that's exactly what I've defined. Now, if I now want to define multivariate normal, if I now want to define conditional, why is the conditional coming in? Don't forget, I have some y values, I got some x values. I may want to look at, okay, if I have information about some x values, what can I say about a particular y value? And that is the reason here, if you take a look at what this guy is saying, please pay attention. You know what that guy is saying? That guy is sending a message. You know the message? is trying to say that's a conditional multivariate distribution. Y given S. Do you see that? This is not just multivariate normal, but this is a conditional multivariate normal. And that is the reason why I said the follow normal distribution in the mu, I put a star, mu star, because that very mu will be computed using a special formula. And I put in the covariance, I put a star. Can you see that? Now, how am I going to figure out my mu star? How am I going to figure out, my variance covariance star? That is what I'm actually going to use. Okay, I have mu star equal mu y. When I say mu y, that mu y is going to be a vector, mu vector for y, right? Okay, plus, you see, inverse of variance covariance xy that I told you is going to be a matrix. Then inverse of, variance covariance for xx, then x minus mu x. Okay, you remember when we're dealing with the bivariate case on Wednesday, when I talk about conditional mean, you know how we figure it out. Okay, now this is what we actually going to use to figure out what the conditional mean is and the conditional variance covariance. Okay, we're still going to apply this, but I needed to pay attention to that. We're talking about conditional multivariate normal here. Okay, now when you take a look at equation 17, okay, now the only condition, please pay attention. You know what I'm trying to say here? Pay attention. What I'm trying to say here, conditional distribution become unconditional distribution. When I say unconditional, I mean the regular multivariate normal distribution. The only condition under which you remember on Wednesday when I said the variance of y given s equals sigma square y 1 minus this, right? Now, the only condition under which this is going to be equal to this is a conditional variable, this unconditional, is when this guy equal to 0. When that guy equal to 0, what do I have? That's a sigma square y. Well, you know what I'm trying to talk about here? The only condition under which, conditional distribution will be equal to the unconditional is when this guy equal to 0. This guy. That guy is the covariance, okay, between x and y. If the covariance is 0, correlation will be 0. That means conditional become unconditional. That is exactly what I mean. Does that make sense? And that mu star is going to be mu of y. If you go back to the equation, if you come back here, okay, and you plug in, if this guy is a 0, right? The whole thing here is going to be 0, and you're only going to have mean of y. You're only going to have mean of y. Okay, and here, the same thing. This is going to be 0, and you're only going to have the variance covariance associated with the y component. Okay, please pay attention. Okay, pay attention. That's what I mean. Okay, now, that's what I mean. Now, I want us to go into an example. Let's look at an example. Okay, each delicious candy company store makes 3 size candy bars. Regular is X1, font size is X2, and big size is S3. Assuming the weights in ounces of the candy bar X1, S2, S3 follow a multivariate normal distribution. Oh my God, I'm seeing a typical exam question here. Please pay attention. Typical exam question. Now, you got a mean. They give you the mean to be this. They give you the variance, covariance to be this. The first question, suppose we select a store at random. What is the probability the weight of a regular candy bar is greater than 8 ounces? Look at that. Here, what are they talking about? They are only focusing on a particular candy. They're only focusing, even though you have x1, s2, s3, but they're only focusing on just one variable. If they're focusing on just one variable, you're going to make use of the idea of univariate normal. Does that make sense? For the first question, we're using univariate normal for the first question. For the second, okay, now now if I want to solve, let me do it one by one. For the first question, look at that. Because they're only focusing on a particular variable, just one variable, then I'm going to go back to univariate. Now, in the univariate, look at that. How do I got this? The mean equal to 5, the variance equal to that. I'm actually going to come back here. This is the mean because you're focusing on that. The mean of that, what is the variance of that? Don't forget I said the variance is occupying this diagonal, then the variance for that is going to be 4. And that is how I know for that particular variable, the mean is going to be 5, the variance is going to be 4. Any question on how I started that? Then I'm just going to go back to normal statistics class where we want to figure out the probability associated, something you've done before, okay, where we're going to make use of the standardization. Now, I want to find the probability of S greater than 8. Look at that, S greater than 8, where I'm going to use the idea of a standardized, okay, where, the standardized, where I'm actually using X, don't forget that, minus mu, over standard deviation, something you've done before. What make normal distribution to be very important is because of simplicity or probabilistic computation, because with normal distribution we're able to standardize. Well, that standardization. Then here now, the probability of z greater than 1.5 is going to be 1 minus that. I can check that from table or using R, P norm, 1.5. Then I'm actually going to get this guy out. I'm done. But that is easy, right? Let's go to question B. Question B. Take a look at the question B. The weight of a regular candy bar is greater than 8. Look at that. Pay attention now. They say giving. Pay attention. Whenever you see a word giving, then you're actually going to use a conditional probability. Now, given that the font size bar weigh 1 and the big size bar weigh 10. Look at that. You want to figure out probability of a particular variable given that you have information about the other two. Then the idea of multivariate is going to be in use. Okay? You see that? Now listen. When the idea of multivariate is going to be in use, before I can use standardization, I need to know the conditional mean and the conditional variance covariance. Because before solving this the other time, before solving this, and four of us know what is the mean and what is the variance. Does that make sense? Now, if I want to, without the mean and the variance, there's no way I'm going to standardize. If there's no way I'm going to standardize, there's no way I'm actually going to figure out the probability associated with that. So, and that is the reason the very first thing we need to do, we need to figure out what is the conditional mean that I call the mean star. I'm going to stop here. I'm going to start from here on Monday. Is there any question before I go? Is there any question? Okay. Happy Valentine's Day to every one of you. Okay. Stay warm. Stay safe. Bye for now.